Today our theme is, at least for part of today, is acids and bases. And we're going to talk about them a little bit differently from the way you maybe learned about them in a general chemistry class. So to start out, how many of you ever learned about acids and bases like this? There's some acid, a Bronsted acid is a molecule that is willing to lose a proton. We would say, well, we'll just keep going with that. And you may have been taught that acids do this. They dissociate, loses the proton. Did you ever learn that? Okay. That was true from a certain point of view, but even Obi-Wan's cop-out can't save us on this one. That is not actually how it happens. Doesn't happen that way in water. It might happen that way in the vacuum of space. But for our purposes, that's way, way, way oversimplified. Because all of the chemistry of biology happens in solution, happens basically in water. And in your blood, that water is pH 7.4. In your stomach, it's around pH 2. And so we need to always be thinking about acids and bases as they would interact in solution. That is, acids don't just randomly dissociate and lose their protons. Instead, acids are deprotonated by bases. By deprotonated, I mean somebody attacks the proton and steals it. Acids are deprotonated by bases. And another way of saying that is the HOMO of the base attacks the sigma star of the bond between hydrogen and whatever this is. And we'll talk about what that is. We're just abbreviating in general whatever acid the group the proton is attached to, we're calling it A. All right? So let me give you an example of an acid-base equilibrium reaction. This is going to involve let's see, this is going to involve HCl as the acid, and it's going to involve water as the base. I'm going to use an equilibrium arrow. If HCl is the acid, or the electrophile, what is the relevant LUMO of HCl? Yeah, that hydrogen chloride sigma star. We won't draw it today because you drew it last week. You know that that's a lot on the hydrogen right about here. What's the HOMO of the base or the nucleophile, which is in this case water? Lone pairs, good. So the way we will draw the mechanism of this reaction, the way you can predict an acid-base reaction happening is the lone pairs attack the hydrogen chloride sigma star at the hydrogen. We make a new bond between oxygen and hydrogen. Because we've dumped electrons into a sigma star, we break the hydrogen chloride bond, and the electrons from that bond go out onto chloride. And what we end up with is H3O plus and Cl minus. Okay? That's an acid-base equilibrium reaction. You always have something acting as a base that deprotonates the acid. So we want to introduce a couple of new terms. If water is the base, as we said, on the other side of the equation, water becomes H3O plus, and we will call water the conjugate acid of the base. The conjugate acid is what the base becomes after it steals the proton. Okay? And at the same time, as we look on the left side of the equation, our acid was HCl. Whoops. HCl gets deprotonated and becomes Cl minus. Cl minus is the conjugate base of the acid. So it's important to be able to look at an acid-base reaction and identify the connections between the left-hand side of the equation and the right-hand side of the equation. This is the acid, this is its conjugate base, this is the base, this is its conjugate acid. Okay? Questions about identifying acid and base, conjugate base, and conjugate acid? Yeah?
So is the best way to start looking at a problem like this to identify which one's a nucleophile and which one's electrophile and go from there?
Yeah, if you want to start an acid-base problem, deciding which one's the nucleophile or the base and which one's the electrophile or the acid, that's a great way to begin. Okay? And you'll notice that you can push arrows backwards from the right-hand side of the equation in exactly the same way we did pushing the arrows forward. You can start with the conjugate base and have the conjugate base deprotonate the acid. That's how reactions go backwards and forwards. Other questions? Yeah?
So the nucleophile will always be the base and the electrophile will always be the acid?
That's right. The nucleophile will always be the base. The electrophile will always be the acid. Yes?
So the conjugate, is that always going to be a product?
Conjugate base will always be the product of the acid. Conjugate acid will always be the product of the base. And all this, what we're doing in this acid-base reaction, we might call these, I call them sometimes proton transfer reactions because the proton used to be attached to HCl, now it's attached to water. Notice that the arrows don't show us where the proton goes, the arrows show us what the electrons are doing. Okay, saw another hand? No? Yes? Okay, now we could ask ourselves, what is the equilibrium constant for this reaction? Which side, which is the same thing as asking which side is favored at equilibrium. If equilibrium constant equals 1, that means the products and the reactants are about the same energy. If equilibrium constant is greater than 1, then that means the products are favored. If it's less than 1, that means the starting materials are favored. We could get more mathy than that, but I think 1, greater than 1, less than 1 may be all that we need to do. What questions do you have about equilibrium constant? Go ahead. Right. If equilibrium constant is greater than 1, that means products are favored. If it equals 1, that means 50-50. And if it's less than 1, that means starting materials or reactants are favored. So asking this question about equilibrium constant is really important because if we know what that equilibrium constant is, we can answer the question, is water a strong enough base to remove the proton from HCl? And so we could do the experiment and measure the equilibrium constants, but it turns out people have done this already and tabulated them. Now, if you know a little bit about equilibrium constants, they vary widely over lots of orders of magnitude, meaning one equilibrium constant might be so small, it might be less than 1, like 0.00000000001, and another equilibrium constant might be 10.5 trillion. So in order to talk about these without having to say large numbers, we use a slightly different method. It contains all the information in equilibrium constant, but it's easier to work with. And that is something called pKa. Now I can teach you about pKa without telling you anything about the math. And I feel like that probably is the way to go. But there's going to be like 1 or 2 people in the audience that are like, oh, I really want to know what pKa means. So if you'll bear with me for just a second, we're going to do a little bit more math than I told you we would do at the beginning of the semester. I told you if you could count and if you could greater than less than, you were pretty good to go. We'll do just a little bit. I think it's worth it so that you understand what pKa means. This is something that students often struggle with, but if you get it down, a lot of things later on in the semester are going to be quite a bit easier. So I'll define the equilibrium constant for us, okay? We're going to just assume we're in writing out a generic equilibrium constant. I'm going to adjust the equation that we wrote above to just some generic acid, not HCl, but just HA. And water steals the proton from HA and becomes H3O plus. A minus is the conjugate base of our acid, which is HA. Okay? So up here, HA is just HCl, A minus is Cl minus. Do you get how we're doing that abbreviation? Okay. If you remember how you do equilibrium constants, you do the product of the concentrations of the products, so the concentration of H3O plus times the concentration of Cl minus, and then over here, on the bottom, you need the concentrations of the starting materials, which are HCl and water. Now it turns out that the concentration of water is really, really large in aqueous solution. It's about 55 molar. So if one molecule of water reacts with our acid, it actually doesn't change the concentration of water very much at all. So we're just going to do a little trick of algebra. We're going to multiply both sides of the equation by the concentration of water. And we're going to move that over there and put it on the left side of the equation where we put all the things that are constant. All right? As the reaction happens, the concentration of water doesn't change very much, so we're just assuming that it's constant, and that's a pretty good assumption. So we're going to call this new constant that we just invented, our equilibrium constant times the concentration of water, we're going to call that Ka, which some people call the acid dissociation constant. Because it's got H3O plus and Cl minus up here, and it's got HCl there. All right? Questions so far about what we've done? It's okay if you don't see the point yet, but do you understand how we defined equilibrium constant and how we moved the concentration of water around? Nobody's saying anything, so I have no idea whether we're okay or not. Okay. Good. All right, so that's how we define Ka. Ka is the acid dissociation constant. And again, if Ka is greater than 1, what that means is the acid loses its proton to water to become the conjugate base in H and Cl minus. Okay, and if Ka is less than 1, I'm wondering if that's exactly true. Okay, well, let me just, instead of saying less than 1, if Ka is large, if Ka is small, that means the acid doesn't lose its proton to water. So Ka is a measure of how strong the acid is. Now, as I said, Ka varies over many orders of magnitude. And so one of the things you can do to make things simpler when you're trying to compare numbers like 10 trillion with numbers like 0.000000001 is you can take the logarithm, the base 10 logarithm and of a number, and that makes it easier. So we're defining the term pKa, where P stands for power, as the negative log of Ka. Do you remember logarithms from high school math? What does the logarithm do? Yeah, it's the logarithm of a number is the number you would have to raise 10 to the power of. That's terrible English. In order to get your number. Anybody say it better than me? So the logarithm of 10 is what? Just 1. Okay, because 10 to the 1 equals 10. The logarithm of 100, 2, because 10 to the 2 is 100, and so on. Logarithm of 1 is 0. 10 to the 0 equals 1. Okay. Logarithm of 0.1 is -1. 10 to the -1 is the same as 0.1. Is this sounding sort of familiar? Don't worry about it. You're not gonna be doing a lot of math, but it's important for you to see where this comes from. So if we do the minus log of both sides, that means that we got to take the minus log of everything here in parentheses. Only I was supposed to be generic, right? I was supposed to put A minus up here and HA down there. Okay, that's fine. Now, one interesting thing you can do with logarithms, there's a property of logarithms that means that if I have two numbers multiplied by each other, it's the same as taking the sum of the logarithms. So you'll just have to trust me on this. This is properties of logarithms. If you don't know sort of where we're going with this or how I did this, that's fine. You can just trust me that the math works. Okay, so we've separated out. We now have the log of H3O minus log of H3O plus, and then still left behind is the minus log of this ratio of A minus to HA. And then lastly, maybe you remember a definition from general chemistry. What we've got there is really just pH. What we've just derived is something called the Henderson-Hasselbalch equation, and it's really useful in biology and not for the same reasons that you may have talked about it in general chemistry. Because what this equation tells us is that if you compare the pH of a solution to the pKa of an acidic group, it will tell you, I'm using another property of logarithms here, by the way, a negative log of a ratio is the same as the log of the inverse of that ratio. So again, if you don't want to know the math, don't worry about it. You can accept what I'm telling you here on faith. But what this equation tells us is if we know the pKa of an acid and we compare it to the pH of a solution, we can figure out what this ratio is there, what the ratio is between the acid and its conjugate base form. And that's an important observation. So we're going to come back to that if we compare the pKa of an acid with the pH of a solution, we can tell what the ratio of the acid form should be to the conjugate base. But pKa basically will tell us how strong an acid is. I'm going to scoot this down a little bit. Do you remember that we said that if Ka is large, an acid loses its proton to water? Or in other words, an acid is strong. Maybe that's how we should say it. If Ka is large, the acid is strong. If Ka is small, the acid is weak. How does taking the minus log of pKa change things? If Ka is large, what should pKa be? If Ka is large, pKa should be smaller. If Ka is small, meaning the acid is weak, what should pKa be? Yeah. This is an important observation that stronger acids have smaller, and by that I guess I mean lower in magnitude or more negative, because there are acids with negative pKa's, stronger or more negative pKa's. Weaker acids, so that's an important principle for today. Stronger acids have smaller and more negative pKa's. Weaker acids have larger, more positive pKa's. And you can use pKa's to determine which side of an equilibrium will dominate at equilibrium. For example, you can look up the pKa of HCl. And if you do, it is -7. You can also look up the pKa of H3O plus, and if you do, it is -2. To compare which side's going to dominate at equilibrium, you identify the acid on one side of the equation and the conjugate acid of the base on the other side of the equation, and you just ask which acid is stronger. So which acid is stronger here, HCl or H3O plus, just by comparing pKa's? HCl, right? Stronger acid. The stronger acid wins by losing its proton. So at equilibrium, we would favor H3O plus and Cl minus. That means when you go buy a bottle of HCl from the stockroom, if you've ever done anything in a lab class, what you're really buying is H3O plus and Cl minus, because in the presence of water, all the HCl loses its proton to water. By the way, the difference in pKa's tells you how much more favorable the right-hand side of the equation is than the left-hand side. This pKa is 5 pKa units. That means 5 powers of 10 higher than this pKa. Means this molecule is 100,000 times more acidic than H3O plus, so of course it's going to lose its proton. Okay, questions you have about that? Yeah, go ahead.
Could you just maybe go over that one more time, like the different pKa's and why H3O plus is weaker?
Yeah, so we haven't talked about why. We just got, the question is, why is H3O plus a weaker acid than HCl? And we actually haven't necessarily talked about that. We've just used data from a table that I looked up. HCl has a pKa of -7. That's much lower than the pKa of H3O plus. Therefore, you conclude that HCl is the stronger acid. And then if you were to ask which side of the equilibrium arrow dominates at equilibrium, the strongest acid wins by losing its proton, and so the right-hand side would dominate. Okay, I saw another hand. Same question, okay. What else? Yeah.
So we were deciding at the very beginning, sort of K, the equilibrium constant, that is not the same thing as Ka, but
It's related to Ka.
okay.
Yeah, Ka equals that equilibrium constant times the concentration of water. So basically what we're doing with Ka is we're taking any acid we can think of, we're putting it in competition with water to see how much hydronium gets made, and then we're writing down the number, and that's how we rank acids. They all get, instead of doing every possible combination of experiments, we do it once, comparing the acidity of whatever acid we're interested in to the acidity of basically H3O plus, and then we find the number, that's Ka. We use pKa to compare all the acids.
So to go from like Ka to an equilibrium constant, so we could see which is bigger, you would just move water back down?
You could, but you don't need to. We're doing that math in an implied way when we just identify the acids on either side of the equation and then see what the pKa's are. And the strongest acid loses its proton. Yeah.
So what would a test question look like?
I'm glad you asked that. What would a test question look like? So one way to do this might be to say, here is an acid. And I might ask you which side of the equation dominates at equilibrium. And I would give you a table. You would first, but before you even looked at the table, you would need to identify the acid on the left side and the base on the left side, and then the conjugate acid and the conjugate base on the right side. So in this equation that I've drawn for you, which is the acid on the left-hand side of the equation? It's the carboxylic acid. You can tell because why? It loses its proton. Which one loses its proton? That's the acid. Okay? Notice, so that makes which one over here is the conjugate acid of the the conjugate base of the carboxylic acid? The one on the right, the negatively charged thing, yes, this is the conjugate base. This is called a carboxylate. It's the conjugate base of the carboxylic acid. So this is our acid, there's the conjugate base. That means on the left-hand side of the equation, water is our base. Water is going to be removing the proton from the carboxylic acid. And that makes hydronium our conjugate acid. All right. So now I would give you a table and you would look up pKa values. In fact, there is a table on the back of your quiz that you can look at. So look at that and see if you can find what the relevant pKa is for a carboxylic acid. Okay, you found it yet? Nobody wants to say because you all know it and it's obvious, or what? 4, okay, good. This is not a rhetorical class. It's not on this table, the pKa of hydronium, because that's a number I want you to know, and that's -2, okay? So, who is the stronger acid? Is it H3O plus, or is it the carboxylic acid? H3O plus is the better acid. How did you know that? pKa is smaller by 6 pKa units. That's a factor of 10 to the 6 in equilibrium constant. Or in other words, hydronium is 1,000,000 times more acidic than the carboxylic acid. Okay, so which side dominates at equilibrium? Starting materials, right? Left hand. Good. Okay. Let's do another one now. We're going to keep the carboxylic acid, but we're going to swap out the base. In this case, in this time, we want to use the following functional group, which is called what from last time? What is this functional group? Amine. Okay. So draw the conjugate base of the carboxylic acid. That's the same as above. It's just the carboxylate. Now draw the conjugate acid of the base, which is the amine. That should be the amine. And if you have a hard time figuring out what it is, start with the lone pairs on the base. Have them attack the sigma star for the oxygen-hydrogen bond on the acid. You make a new nitrogen-hydrogen bond. That means the conjugate acid of the amine should be this positively charged molecule, which is called an ammonium ion. Okay. Now look at your pKa table and see if you can find anywhere an ammonium ion. What have you got? Anything? 9. Okay, let's see, looking at the table, 9 is for NH4 plus. What if one of those hydrogens is an R group? Does the pKa change at all? Look at the table and see if you can find an example where you have a nitrogen attached to an R group, which is usually something carbon, and then 3 other hydrogen atoms. That's 11. In this case, it's not going to change our conclusion, but it does illustrate that you want to find on the pKa table something that resembles as much as possible the situation you're dealing with. The number you would have been looking for would have been this one on the table, or I think it's written out RH2NH with a plus. Okay, so which is the strongest acid, the ammonium or the carboxylic acid? Yep, because the pKa is lower by a factor of 10 to the 7. So strongest acid loses its proton. That means right-hand side is favored. Okay, so yeah, go ahead.
Can you explain how the favor works again?
If you compare the pKa values, that allows you to see which one is the strongest acid. The strongest acid loses its proton, and that means equilibrium favors the right-hand side. And you can get a sense for how much it favors by comparing these pKa values where every pKa unit is a factor of 10. So I see that 11 versus 4, that's 7 pKa units, and by that I infer that the right-hand side is favored by a factor of 10 to the 7.
Did you say that the lower the pKa, the less stable it is, so it won't want to remain in that state?
Yes, you could say that the lower the pKa of an acid, the less stable the acid is. Okay, good. Yes?
So you said that we don't have to memorize this chart since we know it?
Right. Yeah, there's 2 numbers on that aren't on the chart. One of them is hydronium, and the other is water. What do I mean by the pKa of water? Well, what if water were the acid? Let's imagine the amine base deprotonating water. How would that look? Well, if water were to act as an acid, that means the lone pairs on the base would attack a proton and remove it from water. The conjugate base of water would be OH minus, hydroxide. And then the conjugate acid of the amine base would again be this ammonium ion. And we've already said above that the pKa of the ammonium ion is 11. The pKa of water is 16. And this is another number to memorize. I'll highlight those in yellow. -2 for water, -2 for hydronium, 16 for water. Based on that comparison, which side dominates at equilibrium? Reactants, right? Because the strongest acid in this case is the ammonium ion. Its pKa is lower. So yeah, we would conclude that at equilibrium we favor the left-hand side. Okay? So you can use pKa values to make judgments about whether a reaction's reasonable or not. What we've just done, asking which side dominates at equilibrium here, is the same thing as asking, is the amine a strong enough base to deprotonate water? Can the amine deprotonate water? And the answer is no, it can't, because equilibrium favors the left-hand side of the equation. Okay? Other questions? Yeah.
Just to confirm that like the reaction is happening in both directions, like there still is ammonium being created, but it's just at such a slower rate.
So equilibrium tells us that this difference of a factor of 10 to the 5 means there's way, way more starting materials than there is this. Yes, you can find some of that there, but it's very, very small. See another hand? Yeah.
So the conjugate base loses the proton, the conjugate acid gains the proton?
The acid on the left-hand side loses a proton to become the conjugate base.
Gotcha, so in this example, the HO negative, that is the conjugate.
That's right. That is the conjugate base of water. And the ammonium is the conjugate acid of the amine.
Thank you.
Yep, good. Yeah.
So the conjugate base will always have a negative charge and
Will a conjugate base always have a negative charge? That is a great question. And you'll see that the answer is no if I rearrange this equation. I'm just going to put what was on the left, what was on the right now on the left. If we do this, then this is the acid, this is the base. You will see that the amine is the conjugate base of the ammonium, and that water is the conjugate acid of hydroxide.
so the conjugate square will always be on the wrong side and then the acid is.
So yes, the way we've set it up, the conjugate base and the conjugate acid will always be on the right-hand side. But understand it's totally fine to use the term conjugate acid as a relationship between two things. In other words, I could say this is the acid, but it is also the conjugate acid of this base. I could say that Ca is the conjugate acid, but it is of hydroxide. It's a relationship between two things. Let's actually practice that with identifying conjugate bases. There's an item on question 1, asks you to draw the conjugate bases of the following acidic groups. So lots of different molecules shown here. These are all involving functional groups that are really important in biology. And I want you to look at each one and see if you can identify the acidic proton. You're looking for a bond between hydrogen and usually some electronegative atom. And if you are struggling, you can turn the page over and look for those functional groups on a pKa, on the pKa table, and see what you can find. Drawing the conjugate base will involve removing the acidic proton and drawing what's left behind after it gets removed. The first one's a carboxylic acid. That one ought to be pretty easy. Some of the others are going to be difficult. So go ahead and want you to take 3 minutes to draw as many of these as you can, and then we'll work through some of them together. about halfway through your 3 minutes. What you got? Have you got, or you need more time? You doing okay? And it's okay, you're not meant to do all of these in the 3 minutes. I just want you to get as far as you can, and then we'll talk through it. All right, why don't you pause where you are and now compare with a neighbor, and if you got stuck, see if you can help each other out, getting started.
I think so. Basically, basically there's an acid
Okay, let's all come back together. From your discussions, what strategies have emerged for doing this? If you're getting it right, how are you doing it? You don't know if you got it right yet, do you? That's okay. Any strategies that have emerged yet? Yeah.
Just make the hydrogen go away.
Okay. Make the hydrogen go away, and when it goes away, what's left behind? Is it always a negative charge? It's what's left behind is the electrons that are in the bond between the hydrogen and whatever it was bonded to. So whether the conjugate base is going to be negatively charged or not depends on what the hydrogen's bonded to. For example here, and it may help you in doing this, to draw out the oxygen-hydrogen bond and imagine some base actually removing the proton. That helps you remember that the electrons in that bond stay with the oxygen. So the conjugate base for the carboxylic acid should be the carboxylate, where 2 of the electrons on that negatively charged oxygen came from the oxygen-hydrogen bond. Does that help a little bit? Okay, so how about for the alcohol? What is the conjugate base of the alcohol? What should I draw? O with how many lone pairs? 3, and a negative formal charge, and one of those lone pairs comes from the OH bond, right? We'll call that an alkoxide. So how about the thiol? This is one of our skunk thiols. What's its conjugate base? Should be kind of like the alkoxide, only we got a sulfur instead of an oxygen, right? So again, if you need help on that, draw out the sulfur hydrogen bond, show the base attacking the sigma star, removing the proton, and then those electrons go on to the sulfur, which should have a negative formal charge. This one's called a thiolate, and thiolates are important nucleophiles in biology. So this one is weird a little bit. It looks like it's got 3 OH bonds. This is phosphorus. So, sorry, it's not phosphorus. There's a phosphorus in there. This is called phosphoric acid. This is an important acid in biology. What should its conjugate base look like? Or rather, what do you do when there's more than one proton that could be removed? Start with one. Okay, just remove one of them. So if I removed one of them, what would I have? One oxygen that should have what on it? 3 lone pairs and a negative charge. Okay? Good. Now, it is true that there are other OHs here. If I wanted you to draw the conjugate base of this one, what would you do? Go ahead.
How come phosphorus is breaking the octet rule?
Right, phosphorus is totally breaking the octet rule. It is a 3rd row element of the periodic table. It is large enough to accommodate that many groups around it with stable bonds, whereas carbon isn't. Another way of thinking about it is maybe phosphorus is close enough to the d orbitals that it's able to use some of those for bonding. There's some debate about what the right way to think about it is, but yeah.
The same with sulfur.
Sulfur can as well, yeah. All right, what would the conjugate base of this monoanion be? Just take another proton, right? Have another proton, remove it. That would be this one with 2 negative charges on oxygens and 1 OH group. What we're doing here is very similar to what we did with phosphoric acid. This functional group is called a phosphoester. The conjugate base of this phosphoester, same thing, just remove one of the oxygens. And then you see there's also another. If I asked you what is the conjugate base of that monoanion, it would be the dianion. Okay? Yes?
So for the phosphoric acid, is there 3 different conjugate bases, or is there only one of them?
So the monoanion is the conjugate base of phosphoric acid. The dianion is the conjugate base of the monoanion.
So comparing an acid and its conjugate base, you only take away one.
That's right. Comparing an acid and its conjugate base, you always only take the one proton. What we haven't drawn is the conjugate base of this one, but you can figure out what it would be. It would have 3 negative charges, right? This is a phrase you learned to hate and fear maybe in Gen Chem. It was the phrase polyprotic acid, which was almost worse than polyatomic anion. But a polyprotic acid is one that simply has more than one proton that can be removed. We'll see that the pKa's of these protons vary. If I asked you to look up on the pKa table on the other side of the quiz, what would you expect the pKa of the first proton from phosphoric acid to be? Phosphoric acid isn't listed there, but the phosphoester is. They're both neutral, they both look the same, so the first pKa is probably similar. What is the first pKa for going from a neutral phosphate group to a monoanion? What do you think? 2, right? Okay. How about the second? How about losing the second proton to go to the dianion? Do you see any number on the pKa table that would help?
7.2.
Yeah, 7.2. Same thing for the phosphoester. The first proton you lose is 2, the second is around 7.2. That's important. We're going to get back to that. I showed you that weird equation. I talked about comparing pH with the pKa of an acid. We're going to return to that, but what about the thiol? If you looked up a pKa value for the thiol, what would you come up with? What is the answer for the SH group? 8. Right, so we'll write the number 8 as a pKa value by the arrow. For the alkoxide, the pKa, if you had to guess a number that we've talked about already today, the pKa for the alcohol doesn't show up on the table. If you had to guess what it should be close to, what would you guess? It should be kind of like water, right? Though alcohol is like water, in the sense that only one of the protons on water has been replaced with a carbon. So it would be a decent thing to guess that the pKa of the alcohol should be 16, and it is. How about the carboxylic acid? Did you look that one up? Is that on the table? What is the pKa? We've done that already. 4. Okay, good. Of the acids we just talked about, which is the strongest? The phosphoester and the phosphoric acid. Yeah, stronger acids than the carboxylic acid. Good. I want to do, some of these would be good for you to do. This one is really hard. Did you look at that one and say, what the heck am I supposed to do with that? Good. That was the intent. How about this one? You've seen something like that. What is the conjugate base of the ammonium ion? Just the NH2, right? And that pKa, if you look at the table, is what? Good, 11. So notice, positively charged acids have neutral conjugate bases, but the thing you're always doing is removing the proton. Now, this one was probably disturbing to you a little bit. This one is called a guanidinium group. It's important in an amino acid called arginine. You got lots of protons, a neutral nitrogen with a hydrogen on it, a neutral nitrogen with 2 hydrogens on it, a positively charged nitrogen with 2 hydrogens on it, this nitrogen forming 4 bonds. Which is the one do you think you should remove? The one on the positively charged nitrogen. That's a giveaway. That's a key. Look for the positively charged nitrogen. That's the one that can afford to lose a proton. So I would draw the conjugate base of the guanidinium by keeping everything the same, only there would just be 1 hydrogen on what used to be the positively charged nitrogen. This is called a guanidine functional group. That actually, the guanidinium ion shows up on your pKa table. What is it? 12, yeah. Okay, so which is a stronger acid, the ammonium ion or the guanidinium ion? Ammonium, yep, by a factor of about 10. Let's do a couple more. What about this one? What's the conjugate base? Sure, just remove the proton from the positively charged nitrogen. And can you find a pKa there on the table? Anything that looks like, yeah, so some of you are looking at 11. 11 was the number for the ammonium ion. And it is true that that's a decent approximation, but you're going to want to try to find something that is close as possible. Okay, let's see. We had the pKa for the ammonium ion was 12. The number you're looking for, I think, that you saw that was 38, is for the neutral amine going to a negatively charged conjugate base. That pKa is 38. That pKa is high enough that we're not going to worry about it in physiological solution. Amines never lose their protons like that in water. It turns out the pKa for this proton, the positively charged nitrogen attached to this ring, is around 6. Which is the stronger acid? This ion or the ammonium ion? The one that has the pKa of 6, this ion. This one has a name too. This is called imidazolium. Why, any possible explanation for why this acid is more acidic than this one? It's hard, right? So let me share an important principle with you that we're going to use a lot. If you want to explain why something is acidic, consider the stability of the conjugate base. And the key principle is strong acids have very stable conjugate bases. They can lose their protons because the conjugate base that's left behind is quite stable. I'll say that again. Strong acids have very stable conjugate bases. They can afford to lose their protons because the conjugate base is so stable without the proton. So let's compare the two conjugate bases. We already know that imidazolium is much more acidic than ammonium. So now let's consider, we would conclude that the conjugate base of imidazolium happens to be called imidazole. We would therefore conclude that imidazole is the more stable conjugate base and the ammonium ion is the less stable conjugate base. Any potential rationale for that? Any reason you can think of why the ammonium should be less, why the amine conjugate base should be less stable than the imidazole conjugate base? Go ahead.
Is it because there's resonance in this?
So it's true that there's resonance, and we will sometimes use resonance to describe the stability of the conjugate base. But there's a better explanation here. Compare these two lone pairs. What kind of orbital is this lone pair in? Should be sp3 because the nitrogen is surrounded by 4 groups. So it needs to be tetrahedral. How about this nitrogen? What is its hybridization? sp2. Now an sp2 nitrogen has 3 sp2 orbitals and 1 p orbital. Let's count off the bonds that that nitrogen's involved in. 1 sigma bond, there goes 1 sp2 orbital. Another sigma bond, there goes another. A pi bond, what orbital is the pi bond going to involve? P orbital. So therefore, what must the lone pair be in? sp2. Now, how should hybridization influence conjugate base stability? What do you know about s orbitals versus p orbitals? Which is higher in energy? S is lower, p orbitals are higher. Do you remember learning S and the 3 p orbitals like that? P orbitals are higher in energy because they hold electrons farther from the nucleus. And so hybridized orbitals that have a greater percent of S in them will be lower in energy. The sp2 orbital is 33% S. The sp3 orbital is only 25% S. So you'd conclude that the electrons in the sp2 orbital are more stable, they're held lower in energy because of the increased S character of the orbital that holds those electrons. Okay? So this is one way that you can use the stability of the conjugate base to try to rationalize acidity. Imidazolium is more willing to lose its proton because the electrons left behind are held lower in energy in an sp2 orbital than are the electrons in the ammonium ion. Questions about that reasoning? All right, we need a break. We've gone on for quite a while. I intended to move on to talking about alkenes, but I think we still need a little bit more time on acids and bases. So let's take a few minutes and then we'll get as far as we can today on acids and bases.